And it's a great pleasure to be here and to have this invitation and to speak with such a really interesting group of well-established scholars. So the title of my talk is Life Cycle Evaluation of Renewable Feedstocks for Fuels and Materials. I want to start by going over some of the motivation for taking a life cycle approaches. So solving environmental problems requires a systematic approach. You can't really isolate a system like a production facility, a manufacturing facility, a chemical plant, isolate it from the rest of the environment. And in this way, life cycle assessment has emerged over many decades and has gained usage as a systematic tool because it looks beyond the boundaries of individual facilities and tracks the life cycle of products and increasingly of engineered systems and processes as well as activities. I'm going to talk about life cycle assessment, and I'll say more about this diagram that shows the processes involved in a life cycle. I'm going to talk about it in relation to supporting engineering and policy decisions. And I'm going to talk about specifically transportation and transportation energy supply. So most of my career has been devoted to studying transportation in some way or other. When we look at the global emissions of greenhouse gases, as well as in the US, transportation comprises about 34% of greenhouse gas emissions. Currently, or in the past, transportation has been almost exclusively dependent on petroleum resources. And while we are in a period of rapid upscaling of electrification of light-duty vehicles for personal mobility, we will be reliant on liquid fuels for a long time, for long-distance transport, like aviation. In addition, some of the policy context for why liquid fuels and looking for renewable options within liquid fuel alternatives has been a growing area for more than a decade now. Many countries around the world, the US, the UK, Europe, have implemented policies for adopting low carbon fuels for their transportation systems. And in doing so, they have required life cycle methods to benchmark emergent fuels, low carbon fuels, in relation to petroleum-based fuels. So biofuels, and that's what I'm going to spend a lot of today's lecture discussing, have shown promise as an alternative to petroleum-based fuels, but we can also say they present themselves as a double-edged sword, because there are some unintended consequences related to land use change when we move from a energy supply that is fixed and in high quantity in space to one that takes up a lot of land, and that there can be indirect effects related to land clearing and CO2 emissions, greenhouse gas emissions, when we intermingle our energy system with our food system or land, agricultural land, and this can lead to extensification and more greenhouse gas emissions. So in this way, life cycle assessment is really presented itself as a robust tool to estimate the complete fuel cycle of greenhouse gas emissions plus consequences. What is life cycle assessment briefly? LCA was developed formally by the Society of Environmental Toxicology and Chemistry in the late 1980s, and it evolved and became standardized with the International Organization for Standardization in the 1990s, and then further in 2000s. LCA, it follows a 4-stage framework where a goal is defined, data are collected to build models, and those data sets are connected to estimating life cycle environmental impacts. Interpretation is a key method that, or a key component to LCA, in that it allows us to look and use statistics and probabilistic methods to test the uncertainty of models. So it was defined as a technique for assessing the environmental aspects and potential impacts associated with a product, process, and activity. I just wanted to also say that I teach a class, a graduate level class on this subject, and I left it in this slide to say that, in fact, during this COVID year, I taught this course completely online, and we opened it up to other universities, and it was an interesting experience of being able to make offer a course nationally and potentially internationally. So I wanted to make that point. So coming back to the policy context for LCA, so many countries around the world, in the US, have developed and set policy into law for adopting renewable fuels and biofuels. And these biofuels need to benchmark the greenhouse gas reduction on a life cycle basis of the fuel relative to a baseline fuel. And what is a baseline fuel? A baseline fuel is the dominant fuels that are on the market, like petroleum-based fuels, for diesel-operated vehicles, for gasoline-operated vehicles. And that range can be quite wide, as low as 85 grams of CO2 equivalent per megajoule, up to over 110 when we get into unconventional oils. Now, so LCA is used as into actual policy and law, and so that means that we need to use models, in fact, to judge the compliance of new technology that is designated to reduce environmental burdens. Now I'm going to talk a little bit about some of the challenges, and that's actually what most of my lecture is going to be about. Many of the technologies that we are looking at for decarbonizing all sectors of the economy, and I'm going to focus on transport fuels, relies on looking at new technology that are at an early stage of development, what are known as low technology readiness levels. This demands a different type of approach, a specific type of approach to life cycle assessment, where we need to be very cognizant of uncertainties and capture those into models. And I'm going to talk about methods that we use and some specific cases where a lack of data is for building models can render the models difficult to complete. So how we are overcoming these. So I want to say one thing: where does this number 85 to 115 come from? Well, that range, I took it from Argonne National Lab's GREET model, and the GREET model is known as a well-to-wheel analysis for the light-duty vehicle sector, or a well-to-wake analysis for aviation fuels. And what it does is it tracks the complete fuel cycle of a liquid fuel. So from extraction of resources, refining, distribution into the economy, into filling stations, and then and that's known as the well to pump, and then operation in the vehicle is pump to wheel. So that number that I cited, 85 to 115, comes from all of these processes, taking them into consideration for each megajoule of fuel dispersed. Now, when we talk about biofuels, so I'm going to use this figure and use the same analogy. When we look at advanced biofuels are completely oxygen-free molecules that are same in molecular composition as petroleum-based fuels, but they are derived from biomass resources. A life cycle model for a biofuel needs to consider the fuel cycle, in this case, collection of the feedstock, which is occupying land, withdrawn from land, converting to liquid fuel, and then operation. So I'm going to talk specifically about advanced biofuels. These are, again, fuels that are completely oxygen-free. They're known as infrastructure-compatible fuels, and they are also derived from biomass resources. So let's take a look at different technological pathways for converting biomass to fuels and chemicals. So biomass, lignocellulose, is comprised of cellulose, hemicellulose, and lignin. There are two routes that one can invest into platform: the biomolecular route, which is the conversion of cellulose and hemicellulose into fermentable sugars that can be then converted into fuels, chemicals, materials, the building blocks of a bio-based chemicals economy. And there's also thermochemical. I've worked in both areas, but I'm going to focus on the fermentation pathway today. So now a little bit about prospective life cycle assessment. So prospective LCA is an ongoing area of research in LCA where we are concerned or interested in new or future-oriented technology. I've listed a number of different papers that have been published in recent years that have described different methods. Also, the name anticipatory LCA has been used. And as we recall from the four-stage framework, prospective LCA can actually influence all of the four stages that I described. So what is prospective or ex-ante LCA? So it's increasingly used for evaluating the environmental impacts of future-oriented technology, early stage technology, and technologies that are at a low TRL. So recall what a TRL, technology readiness level, was defined by NASA in the 1980s. And it's a scale that we see here that shows the progression of technologies from ideas to lab scale demonstrations, sometimes bench scale or computer simulations, to pilot plants and then full-scale operation. So bringing these technologies into the economy. We have challenges in LCA in that we want to develop robust and reliable methods for low TRL technologies to guide whether these technologies are appropriate for investment and whether they can achieve their goal of decarbonizing the economy or greening industry. Given that in these systems there is a lack of real world data, we are really forced to take the path of simulation, computation, and building models from material balances derived from laboratory experiments. This then comes back to the underlying methods of creating mass and energy balances, the thermodynamic models. And these are the building blocks of life cycle assessment. So this is the approach that I'm going to describe today. There's also a vast and emerging literature on different approaches. Some groups are using machine learning to predict new technology environmental impacts based on similarity and what we know already. Okay, so I'm going to talk about now lignocellulosic fuels. What I defined lignocellulose, sustainable forms of biomass can consist of agricultural and forest residues, mill residues, agricultural residues, including animal waste, and energy crops grown on marginal land. When we go down the biomolecular pathway, we are looking at advanced biotechnology that uses enzymatic hydrolysis to decompose the cellulose into fermentable sugars. And there are different molecules and proposed fuels at different levels of technological development that include laboratory, process development unit, as well as demonstration scale, so and higher. So lignocellulosic ethanol is, in fact, was under early stage technology for many years, but it's now an commercial venture. So some of my early work really focused on biomass to ethanol, and I looked at forest and agricultural residues and different technologies, different pretreatment technologies coupled with enzymatic hydrolysis and fermentation. What that looks like is, the basic model for a biorefinery. Now here it's ethanol, but it can be any other type of molecule that can be synthesized. Your feedstock comes in, it's pre-treated. At the pre-treatment stage, lignin is fractionated and sent to a treatment facility where it's burned and for energy recovery to supply steam and electricity for the biorefinery. The cellulose and hemicellulose sugars that are released at the pre-treatment stage are then, they undergo enzymatic hydrolysis and fermentation, in some cases simultaneously, and that there are different orientations for that. Then you have your ethanol recovery fractionation stage, and the model biorefinery here produces mainly ethanol and electricity as a co-product. So we're currently in my group, we were looking at an advanced fuel and jet fuel. So I mentioned in the beginning that aviation fuel will be liquid fuel dependent for the foreseeable future. So in my group, we are looking at an alternative product, DMCO production from through fermentation of C5 and C6 sugars, following the same biorefinery concept, except we are focused on the jet fuel production, but electricity and is also a co-product. Here we are looking at the direct fermentation of isoprene. So in an earlier paper by a former PhD student, we were looking at the fermentation of glucose to methyl butyl ether and its subsequent separation and dehydration to isoprene. Isoprene can then be flexibly produced to jet fuel, as well as polymerized to polyisoprene. And in ongoing work, we are looking at the direct fermentation of isoprene from C5 and C6 sugars. So I want to compare some of these results today and also contrast them with ethanol work we had done earlier. So in our, so I'm jumping to the results now, life cycle greenhouse gas emissions. When we compare our direct fermentation pathway to DMCO and our intermediate fermentation pathway through MBE, we see actually after some optimization of the fermentation unit and the heat integration, in fact, you can save a lot of energy. And when you do that, you can actually co-produce more electricity And that's what leads to a more negative fuel compared to the intermediate production. I said I gave the title to this talk to be about fuels and materials, so I want to also talk about the possibility of producing polyisoprene from corn stover using the same platform, direct fermentation of sugars and their subsequent fractionation and polymerization to polyisoprene, and compare that to natural and synthetic rubber. So natural rubber, although natural, it is also very land intensive, and it has led to a lot of land clearing in Southeast Asia. And so that kind of land clearing is not necessarily a sustainable path for rubber production. And so the synthetic biology approach, where we could use agricultural residues like corn stover, could have some promising elements in terms of greenhouse gas emissions and other impacts, land use, compared to natural rubber and synthetic rubber. So when we do the process modeling for that technology and integrate it into a life cycle model, here we have polyisoprene production from the direct fermentation of cellulosic sugars, and through the earlier work through our intermediate methylbutyl ether, and all of these other contributions to life cycle greenhouse gas emissions. These are cradle to gate, all of emissions up to the production, take into account all of the effects of the harvesting of the feedstock, any changes in soil organic carbon from removing agricultural residue from the land, and fertilizer replacement on the land. And that's why we have some positives, but we have a large sequestration of carbon from the material itself, and still more of the embodied CO carbon from that sequestered carbon in the isoprene itself, in the polyisoprene. And that is what renders these two possible routes negative compared to natural rubber and synthetic rubber. In the case of natural rubber, you also have some embodied carbon, biogenic carbon, but other emissions for its production are render its net emissions to be positive. The other important note is that we also have the co-produced electricity that is part of a credit to the system. So I want to now shift and move on to talking about more methods in life cycle assessment and for early stage technologies. When we talk about transport fuels, there are many tools available for doing life cycle calculations. I mentioned the GREET model. There's GHGenius is a tool in Canada. I'm from Canada originally. EcoInvent is a Swiss tool. There's also tools or data sets from the in Europe from the JRC. And so there are tools and databases and data sets for characterizing biofuels that are emerging and early stage. But when it comes to looking at new technologies and say molecules, like new possible routes for producing alternative jet fuels, we need to actually turn to more bottom-up approaches. And here we turn to chemical process modeling and simulation using a variety of tools like Aspen Plus, SuperPro, Unisim, FactSage, depending on the chemistry of the system. So the work that we were doing was using Unisim, and earlier work I did use Aspen Plus. And here, though, these types of models require an input of thermodynamic data that are measured or available in literature. From there, you can project, build Monte Carlo models to understand uncertainties in the life cycle of the fuel system. And so when you can characterize input parameters, there are many different types of uncertainty, but we're focused on input parameters to the mathematical models for estimating environmental impacts. We can run a Monte Carlo model multiple times and generate stochastic outcomes of different environmental metrics. And so I'm focused on greenhouse gas emissions. If we come back to our system here related to isoprene or isoprene plus jet or jet fuel alone, and we look at the range of uncertainty in the case of this feedstock, looking at corn stover, that's the residue of corn production, including even drastic soil organic carbon losses, we see that, at least to the best of our knowledge with the data we have to build Monte Carlo models, these different pathways are actually lower than the petroleum alternatives as well as natural rubber. So again, to some methods in life cycle assessment, back to biofuels, I want to talk a little bit about some of the other systems that we've looked at. Here we have advanced fuels, renewable diesel, using, again, another early stage technology that employed saponification, decarboxylation, hydrocracking, and finally distillation to produce renewable diesel. And in this case, we looked at biomass sorghum. Using the same kinds of methods that I described earlier, we took the life cycle, we estimated life cycle emissions based on laboratory scale and projected optimized full-scale production. And you can see that the reduction, remember that number 85 to 95 to 115, the reduction in greenhouse gas emissions is not as pronounced as we saw with the renewable jet fuel. And why is that? Just to highlight the factor that is contributing, there's, rather than having co-produced electricity, there's a need for more electricity because it's energy intensive, and an indicator of the need to do much more optimization of the process design to render it feasible for full-scale production. When we looked at the costs, they are incredibly high when using biomass sorghum as a feedstock. If using a lower cost biomass resource like forest residues, mill residues, this large cost can decline also significantly. But you can see here that distillation and solids recovery is very, very energy intensive in this process because it is a dilute system. And so there is energy needed to fractionate. With that, we turn to looking at ready sources of fats and oils using the same kind of technology and coupling the technology in rendering facilities. So the same saponification, decarboxylation, hydrocracking, and distillation. And here I want to talk about some of the approaches that we tested for building life cycle assessment models. So once again, if we come back to that hierarchy I presented earlier related to process modeling and simulation and the need for thermodynamic data. That is the case here, where animal fats have free fatty acids and triglycerides that can be converted into waxes that can then be hydrocracked and converted then to renewable diesel. When we did the energy balances, the thermodynamics in this case, we ran into some data gaps. So back to this hierarchy, the lack of thermodynamic data can make it. How do you overcome this? So in fact, this is what led to an idea that we're actually testing at a greater scale through a recent grant from the Israel Science Foundation, which is to use computational chemistry methods to simulate missing data, and through ab initio calculations, and then use the data that are simulated to incorporate into process models and then into the LCA platform, as well as the build Monte Carlo models. And so in fact, we did just this with the saponification reaction, where the fatty acids are converted, undergo saponification. So we used ab initio methods to calculate the enthalpy of reaction for the neutralization of different fatty acids in the mixture, palmitic and stearic acid, to sodium hydroxide to form sodium palmitate and water. And so in this case, we used ab initio, electronic energy and vibrational energy, 0-point energy to make those calculations, and from there integrate them back into the chemical process models, and from there into the life cycle models. And there we have our estimates of greenhouse gas emissions when we set these all together. And just as a reference to the renewable diesel from biomass that can also make free fatty acids through synthetic biology, if you can get them already made from as a waste, in fact, your emissions are much lower, and that is due to lower process energy and lower energy for fractionation and synthesis and fractionation. So I'm coming now to the conclusion of this talk, and where is this research going, or what have we learned? That LCA models are really important for benchmarking new technology, in this case, biofuels, as alternatives, low carbon alternatives to petroleum-based fuels. And we see from a lot of the work that I've presented some promising developments like renewable jet fuel, but we see vast differences among feedstocks and conversion technologies. In the case of waste, fats, and oils, although they are limited in supply, they can, in fact, meet near-term policy goals because they're readily available. And it's important to note that there are many technological challenges for R&D in advancing through the TRL. And that prospective approaches in LCA are really helpful to help understand the cost and environmental trade-offs of scaling up and overall investment. So to conclude, I want to summarize a few things about life cycle assessment of emerging technology. We are seeing that there's a very interesting role for combining computational chemistry methods in early stage sustainability evaluation. And I think this is an opportunity also through this Vebleo lecture series to collaborate with experimentalists and computational chemists to bridge, to use these really fascinating tools, molecular dynamics, ab initio, density functional theory, to help guide renewable energy and life cycle assessment as a policy. And so I think these methods are quite interesting and more broadly applicable to other technologies. I've spoken about biochemical conversion. There are thermochemical conversion technologies that can also produce fuels and polymers. There are emerging technology in solar PV like perovskite materials, and many, many more. So I just want to add one last caveat that although I was very focused on greenhouse gas emissions, there are multiple sustainability metrics that can be used, measured, predicted through life cycle assessment to estimate the greenness of alternative technologies, products, and engineered systems. So thank you very much. I just want to thank the hosts for inviting me to give this lecture, and also acknowledge the great people who helped do this work, my postdoc and students at the Technion, and earlier students. Previously, I was at Drexel University in Philadelphia, and collaborators from industry, Technology Holding, and Ceramatech. And thank you very, very much. Here is my contact information, and I'm happy to take questions.